Sorry, HOD called me. Sorry. Yeah.
I know, sir. Sorry.
So we have to select our separation process based on the nature of our product from the reactor. Okay. For example, if it is solids are suspended in liquid or gas, then we will select the separation technique called filtration. Okay. Sometimes we can go for settling or sedimentation. Sometimes centrifugation. So if it is gas solid, we will go for cyclones. Okay. So we will go, we will select these type of things. Or sometimes if we have two immiscible systems, then we will go for phase separation using centrifugation, those things, or decantation. You can call it as a clarifier. Okay. So different type of techniques we can select based on the nature. Okay. But some of the mixtures we cannot separate based on these mechanical techniques. Okay, using a physical separation process. Okay, such a cases we need to use some external agents like mass agent, or you can say energy agent. Okay, you have to add the third component, that is called mass agent, so that we can separate it. Or sometimes you have to supply the heat, then you have to generate the vapor. This vapor and liquid will contact, then you will get a separation. Okay, so this is like these things, the principle of these type of separations. Majorly you might have discussed in mass transfer or equilibrium stage operations. Okay, so here the mass transfer, this transport of a species is taking place from one point to another in a single phase, or from one phase to another phase. Okay, the well, based on the concentration difference, or you can call it as driving force. Sometimes pressure difference will also be the driving force. Okay, so you might have discussed different, so many applications of these mass transfer operations in your inorganic chemical technology or organic chemical technology during your fourth semester or fifth semester. Okay, so in mass transfer you might have studied the fundamentals like different type of mass transfer operations, basics. That's like diffusional mass transfer, or which is equivalent in heat transfer, like conductive transport. Okay, or you can say convective. The other one is convective mass transfer, where mass transfer occurs in a fluid medium which is in some sort of motion. By creating some sort of motion, the mass transfer takes place. Okay, so mass transfer is one of the transport process, as like other transport process, momentum and heat. Okay, so the physical laws governs the rate of transfer are almost similar for momentum, heat, and mass transfer. Okay, so whatever the laws, physical laws that you have discussed. So this might be discussed in analogies, different types of analogies you might have discussed in heat transfer or mass transfer. Okay, so here by providing the conditions are similar, you can use the data of one transport. For example, if you have the data of momentum transfer or heat transfer, you can predict the type of mass transfer. Okay, or you can evaluate how much mass transfer takes place using this analogy, like Reynolds analogy, Prandtl's analogy, Chilton-Colburn analogy. So many analogies you might have discussed. Provided the conditions of both the transfer operations should be same. Okay, the conditions should be identical, steady state. So many assumptions are there. If the assumptions are matched, then you can use the transport of one phenomena. Then you can predict the transport of other species in other phenomena. Okay, so that's the idea. Okay, so many analogies are there, like Reynolds analogy. This is the very basic analogy. Then Prandtl modified this analogy. Then Chilton-Colburn analogy, von Karman analogy. So you have so many analyses. So one by one they have modified. Initially they assumed laminar, then they introduced turbulent, then they introduced viscous sublayers, then eddies. it was modified. Okay, then finally they end up with the Chilton-Colburn analogy. Okay, so you have a data for one transfer operation. You can predict the another transfer operations provided so many identical conditions. Okay, so here in this case in separation and purification, that is the second stage of your onion diagram. Okay, so the separation normally it's a simple process because the if you calculate the cost 40 to 70% of both capital and operating cost are required for separation of mixtures. Okay, but if you want to go for high value added product, or if you want to go for purification, then if you want to, then 90% of the operating cost of the plant is taken by this type of purification operation. Okay, so even in distillation column, to estimate the number of stages, you might have used two different methods. One is Ponce and Savarit method, another one is McCabe and Thiele method. In McCabe and Thiele method, when you calculate the number of stages, then you can easily calculate the number of stages, or for till 90% or separation 90% of purity, you can calculate the number of stages. The 90 to 95%, then this operating line and equilibrium line will be very closer. And if you go for this stepwise method, okay, step by step procedure method, then you need more number of stages. Okay, so this more number of stages, this 90 to 95%, sometimes this number of stages required for this separation will be very much higher than the number of stages required to achieve 90% separation. Okay, so when you go for a higher concentration, high purity, or higher value added product, the operating cost will be more for these cases. Okay, so the core separation process, if you see in mass transfer operations, so the core separation process is like absorption, then stripping, then adsorption, crystallization, distillation, drying, extraction. In extraction, you may have a liquid extraction or liquid solid extraction. In humidification, dehumidification. So you have involved with many mass transfer operations. Okay, for purifications or separations. Okay, or transfer of one particular species from one phase to another phase. Okay, so here it may be a gas liquid operation, or vapor liquid operation, or liquid operation, or liquid solid operation, gas solid operation. Many things are there. Okay, so if it is a gas liquid or vapor liquid operation, so it may be absorption, or stripping, or distillation, or humidification, or dehumidification. So these unit operations comes under this gas liquid or vapor liquid. So what is the difference between absorption and stripping? Any one of you, can you please say what is difference between absorption and stripping? Any idea? Hello? Am I audible? Hello?
Sir, audible, sir.
Yeah. So what is the difference between absorption and stripping? Any example for absorption?
Sir, sponge absorbing water, sir, when we put it in water.
Which one?
Sponge, sir, sponge absorbing water, sir.
Oh, you mean it's a solid liquid operation?
Yes, sir.
Absorption is solid liquid operation. AB, I mean AB.
Sir, no, not sure, sir. I'll check and tell, sir.
The solid liquid operation is absorption, AD. Absorption is vapor liquid or gas liquid operation. Okay. So, for example, separation of CO2 from synthesis gas, ammonia synthesis gas. So, here we have to separate the CO2. So, you have to use some solvent. So, that is called ethanolamine, or you can say monoethanolamine. Sometimes you can use carbonate or bicarbonate. Okay. So, that can be the CO2 can be taken from this mixture, ammonia synthesis gas. So, you have to use one more agent, that is called mass agent, or you can say solvent, to absorb the solute. Here CO2 is the solute because that is our target molecule. Okay. So, you can use a solvent, ethanolamine. So, the affinity of this solute towards solvent will be more. So, it will take the solute from the mixture. Okay. So, that is gas liquid operation, or you can say vapor liquid operation. So, actually what are all the phases involving in solvent extraction? Any idea?
Sir, like in extraction?
Solvent extraction.
No, sir, liquid phase?
Yeah, both are in liquid phase. So, is there any extraction which is having solid phase? So, what is the exact
Leaching.
terminology?
Leaching, sir.
What's
Yeah.
happening there? Leaching.
Sir, like the example is, sir, the metal ores, sir, we extract, na, sir. The solid, we extract metal ores. So the solute is being transferred from the solid phase to the liquid solvent, sir.
Yeah, that in day-to-day life also you can see this coffee or tea. Okay, so tea shop you can see the tea dust will taken in the tea bag. So if you pour or if you take the solvent at its boiling point, then what will happen? It will take the tea, or you can call it as decoction. So decoction is type of leaching. Okay, so these are all some examples. Okay, so what's happening in distillation?
Sir, we separate the components based on the distribution of the component in liquid phase and in vapor phase, sir.
Using the
Based on
concept, yeah,
relative volatility difference.
relative volatility, because difference in volatility of a component over another will help to separate this. This is called fractional distillation. Okay, so you will supply the heat. When you supply the heat, this you have two different type of miscible system. Okay, liquid system. Based on its boiling point, one will become vapor. More volatile component will become vapor. So this more volatile component migrates into the vapor phase. Then the less volatile components migrate into the liquid phase. Okay. So more volatile component increases up the column as vapor, then it is condensed and separated. Less volatile components increases down the column and it again heated. So this vaporized more volatile component, sometimes it may have a less volatile component. So it's continuously contacted with the vapor phase. So the more volatile component is transferred from this less volatile component mixture to the top. Then this less volatile component is transferred to the bottom. So you will get it. The separation based on the relative volatility, or you can say the boiling point of the system. Okay, so these are all different type of things, different type of separation. For example, solid liquid, as I said, sometimes apart from this leaching, you can have this gas solid operations. You can call it as drying or absorption. Okay, then you may have this liquid solid separations. You may call it as leaching, sometimes crystallization. Okay, So sometimes you can say absorption. So you have so many different type of interface mass transfer operations. Okay. So here the separation process is different based on separating agent. Okay, for example, in absorption stripping, solvent is the separating agent. In distillation, heat is the separating agent. In liquid-liquid extraction, you have to add the solvent, that will be the separating agent. In solid liquid extraction, you have to use the solvent, that is the separating agent. In drying, heat is the separating agent. This is a very good example for simultaneous heat and mass transfer. Anyway, we will discuss this design of dryer separately. Anyway, here we have both heat and dry gas. Both are is being used as separating agent in drying operation. Then in adsorption, you have to add the adsorbent. That is solid. You have to use to separate the solute. In the case of ion exchange, you have to use ion exchange resin. Sometimes in crystallization, you have to use heat. Okay, you have to use the heat. Heat is the separation agent. So supersaturation, then followed by the formation of new solid particles. Okay. So then sometimes membrane separation, you have to use the membranes, selective membranes. Okay, membrane barriers you have to select to separate the molecules based on size and so many things. Okay, so design of these mass transfer equipments, we need a very good understanding of these principles involved in a particular unit operation, and the construction operating principles of separating equipment is a must. Okay, then only you will get a proper separation. Okay, so I request you to reference the points, whatever you have learned in mass transfer operation, mass transfer and one and equilibrium stage operation, like molecular diffusion, how this is taking place, okay, at what condition this molecular diffusion takes place, okay. So what are the basic governing laws of this molecular diffusion? Just you can reference these things like fixed law of diffusion. You can say this flux is proportional to or rate of flux, or flux you can say driving force by the resistance, or you can say Na is equal, Na is proportional to your driving force, that is dCA, and inversely proportional to your resistance, that you can call it as a distance, dZ. Okay, so you will introduce a proportionality constant, that is called diffusivity of the molecule, diffusivity of one molecule from the liquid mixture. Okay, then you extended this concept for like convective mass transfer. So if you have a sugar and milk in a particular tumbler, so if you keep it as it is, what happened? The mass transfer takes place by diffusion. If you use stirring or some other mechanism, okay, then what will happen? This mass transfer rate is enhanced by this mixing operation. Okay, so here this mass transfer takes place by convection. This may be by natural convection or by forced convection. Okay, so the convective mass transfer is strongly influenced by this flow field. Okay, so mass flow rate can be calculated if the flow field is well defined. Okay, using mass and momentum balance. So you might have studied these things in your transfer operations and also in transport phenomena. You might have modeled for different conditions. Okay, so anyway, during this fifth semester or sixth semester, you might have compared this heat transfer and mass transfer operations. You identified so many similar ideas involved in heat and mass transfer. Anyway, I request you to go through these basic concepts once again, and you compare these different transfer operations and analogy between these things. So once you study the convective transfer, then you might have studied how this mass is transferred. Okay, so you might have studied like different theories of mass transfer, like film theory, penetration theory, then surface renewal theory. So this film theory is the very simple theory. So actually, as per this theory, film of thickness, very small thickness delta, or you can say CS thickness, is formed at the interface. Okay, so this will act as the conductive resistance, or you can say the transfer is taking place by molecular diffusion. Okay, so here this film will offers the maximum resistance to mass transfer. So this overall resistance, order of magnitude of this overall resistance is almost same as the resistance of molecular diffusion. Okay, here the time required to reach the steady state is very small, or you can say negligible. So that's why in film theory, this mass transfer coefficient K is expressed in terms of diffusivity and the film thickness. But the practical problem is that we cannot calculate this delta. Okay, experimentally this is a model parameter. So here this K is inversely proportional to this delta power minus 1. But in the case of this penetration theory, which is proposed by Higby, so you can call it as Higby theory in 1965 for unsteady state mass transfer. Here, he assumed that since sufficient time is not available for the solute to not available to reach the steady state, he expressed the flux in terms of time, dynamic one. Okay, that is dCA by dS. Then this n average is calculated when you integrate over the time period 0 to t. Okay, so in this case he obtained the relationship flux is proportional to root of or you can say mass transfer coefficient is proportional to root of d. In previous case it's 1, now it is 0.5. Okay, so then Danckwerts, who proposed this surface renewal theory, so he didn't assume this laminar sublayer. Then he mentioned that liquid eddies are generated in the turbulent core and migrate to gas liquid interface. Then where this solute exposed to gas for short duration of time. So this this is taking place in very small time. Okay, then the circulation of eddies takes place. The solute is transferred from one phase is another phase. So continuously the new surface is created. So your flux, he introduced one more model parameter, that is surface area renewed. Okay, so that is flux. The equation is slightly modified. That is Na is equal to root of dAs times of delta C, where K is the mass transfer coefficient. Flux can be expressed K into delta C. So this K is root of dA, yes, where we included the another terminology called surface model parameter, surface renewal factor. Okay, so this is very difficult to estimate. So but they calculated the surface renewal factor based on singularity observation. So it is generated by statistical means. So for short exposure of time, this mass transfer coefficient K is proportional to d power 0.5. So experimentally, then they modified this the relationship between K and D. That is K is proportional to d power n, where n varies from 0.8 to 0.9. Okay, this thing. Then once you have studied this mass transfer theory, then you might have discussed about this interface mass transfer by calculating this mass transfer resistance. Okay, two film theory, so many things you might have studied in your mass transfer. Okay, so whatever may be, so this for mass transfer operations, successful mass transfer operations. Okay, whatever, whether it is a gas liquid or vapor liquid or liquid or liquid solid, we need we have to create the space for contacting these phases, liquid phase and or whatever the phases involved. So we have to make the intimate contact between the phases in a particular contactor. So we need a contactor to make these phases or solute or solvent to contact. Okay, then we have to focus to increase the mass transfer rate. The solute transfer takes place at the higher rate. So for that we have to make suitable arrangements in the contactor. First we need contactor to create for interface mass transfer. Then this interface mass transfer should be happen in a higher rate. So we need high mass transfer rate. We have for that we have to go for higher degree of turbulent or mixing. Okay. Okay. Then another one is this interface mass transfer or intimate contact can be done by dispersing the one phase into the another phase. So sometimes gas phase can be the continuous phase, sometimes a liquid phase can be the continuous phase. Okay. So are you able to see my slide?
Yes, sir.
Yes, sir.
So here the main objective is that if this is the contactor, it can be a tray column. Okay. So here we are handling this gas liquid or vapor liquid absorption, or you can say absorption. The vapor is going from bottom to top. The liquid is coming from top to bottom. Okay. So this tray is the heart of this tray column. Okay, so this will provide the contact between this vapor phase and liquid phase. The solute has to be transferred from the vapor phase to the liquid phase, where liquid is the solvent. Okay, so the concentration difference between vapor, this vapor is rich in solute, this liquid is lean in solute. Okay, this solvent is lean in solute. So this will create delta C. So the solute is transferred from the vapor phase to liquid phase. So here you have to provide a contactor for this intimate contact between these phases, and you have to increase the rate by provide suitable mixing. Sometimes you can increase the surface area if you disperse the solute in the liquid medium. So the surface area, or you can say interfacial area, will increase. So this you should interface and interface, these two are different. So this okay. So this you should know the difference between these two terminology, interface, okay, and you have to interface these two. Okay, so the interface means this is between two phases. Interfacial means here you have a bubble. Okay, so the vapor is dispersed as a bubble, so it is surrounded by the liquid. So this area is called interfacial area. So you have to, so if you have many number of small bubbles, then you have more surface area. So your interfacial area will be more. The transfer of solute from vapor phase to liquid phase will be more. So this is the main objective of any gas liquid contactors. Okay. So here you have a different type of contactors like sieve tray, packed column, bubble column, spray column, agitator contactors. You have different type of things. Okay. So the selection of these contactors are normally based on these two parameters: superficial gas velocity and mass transfer parameters. So this A star is the interfacial area, that is meter square per meter cube of the contactor. The surface area or interfacial area generated per volume of the contactor. So your mass transfer coefficient should be in the higher side, and you should have once you have a higher interfacial area, your mass transfer coefficient will also be in the higher side. Okay, then the superficial velocity, because here we have to provide the turbulent mixing, high degree of turbulent mixing. So that can be providing the velocity, because this tray column, no. So you might have studied this tray stability or operating regime of tray column. Those things you might have studied. Anyway, we will discuss those things later part of the discussion. Okay, why how this superficial gas velocity plays major role in gas liquid contactors. Okay, so here we have three different type of contactors. One case is like a tray column, bubble column, agitated vessels. Here your liquid will be the continuous phase and gas is dispersed. So agitated vessel means you have a vessel, so liquid is filled, then you will send the gas through sparges. So the sparges will create disperse the vapor in the bubble forms. Okay, so the contact between the bubbles and liquids will enhance the rate of mass transfer. That is happening in agitated vessel. Similarly, in tray and bubble columns, so you have a tray. So tray will have will act as a one stage. Okay. So here the vapor will go from the bottom. So you have a liquid that will come from the top. Okay. So this you have so many another provisions like sieve tray or ball tray or bubble caps. So through this the vapor will flow, and once it flow through these holes or these things, it is dispersed. So again here liquid is a continuous phase, your vapor is a discontinuous. But in another case, these columns like spray towers, venturi scrubbers and factory towers, what will happen? Your gas phase will be the continuous one, the liquid will be dispersed in the gas phase. So once the liquid flow through these factory towers, you have a suitable packing medium. Okay, so the liquid will flow over this packing and will form a film. Okay, so this may be a continuous film or a discontinuous film because you have dead zones when you go for these packed columns. Okay, so when the vapor flows up, this is a continuous one, this will contact with this film and the solute transfer takes place. But this is the another contactor, falling film contactors, where both the phases are continuous. So you have a column. So here your liquid will go as a continuous one. So you have to allow the liquid to flow through the wall. So wetted wall column or these things, falling film contactors are very good example for these type of contactors because both the phases are continuous one. Okay, so it will flow like this. So this will flow like this. So the solute transfer takes place based on the concentration different. So we have a different type of gas liquid contactors. Okay, so here in the subject we will discuss about the design of tray columns, bubble cap columns and packed columns. Okay, so these three things we will discuss. If time permits, we will go for other type of contactors, agitated vessels, those things, and also the selection based on whether it is a continuous one or a batch vessel. Agitated vessels normally be used for batch, or you can say this bubble columns. Bubble column means you have columns, you have liquid medium, so you have to send the vapor through the distributors, or you can say sparges. Okay, sometimes you may use helical things. So continuous okay, so this is these are all different type of columns. So here based on the requirements you can select the type of contactors. Okay, so in tray column we will discuss about wall tray column, sieve tray column and bubble cap columns. So this bubble column and bubble cap column are different. Bubble column means this is a tall column where the liquid is filled, the vapors are dispersed in the liquid. That's why gas dispersed liquid contactors. Okay, so this is your we will start with this tray columns, or you can say our discussion start with tray columns. Okay, so this tray column you have if you see this diagram, you can see the different components of tray column. So the cell is the important part, that is a major component. Then inside you have a tray, that is another major component. So this tray will help for intimate contact between the phases. Then you have to make provisions in the tray by providing the holes for the flow of vapor. then we have to maintain the minimum amount of liquid in each tray, then only the separation will be efficient. Once the separation is over, then we have to give the provision for the liquid to flow through the next tray. This is the continuous one. So the downcomer is the another major component. Okay. So here for vapor flow, you can provide sieve type of holes. Okay, you can make holes on the tray, or you can provide bubble caps. Okay, or you can provide the valve tray columns. So valve tray columns are the combination of these sieve tray columns and bubble cap columns, variable area columns. Okay, then apart from that, you have to provide these trays has to be supported using the tray support rings, that is like section L section. Okay, so the tray supporting rings has to be provided. If column is very big, then you have to provide beam support. So if this is the column top view, you have to provide the beams. Over the beams or these sections, you have to support the rings when the column is higher diameter. Okay, otherwise you can support the trays using this tray support trays. Okay, so this is downcomer. So the downcomer will help the liquid to flow from one tray to another tray. These valves or sieves or bubble caps will help to flow of for the flow of vapors, and it will also disperse the vapors in the liquid medium. So we have to maintain the minimum amount of liquid in the column. Okay, that is taken care by these wear plates, this W. Okay, so where D is the this W is the wear plate, this DC is downcomer, this DP you can call it as a downcomer plate. Okay, so apart from that, you have to provide the nozzles, inlet outlet nozzle, gas in, gas out, then liquid in, then liquid out. Okay, then this column has to be supported with suitable supports. They may be skirt support or column support, those things. Okay, so different type of supports we will discuss the mechanical design of vessels. Okay, so this is then this D is called demister, which means that when the liquid droplets goes out, sorry, this vapor bubbles go out, sometimes it may take the liquid droplets. So the gas out should be a pure vapor. It should not carry any liquid droplet. So entrainment of a solute or liquids should be very small. So you have to check this entrainment points also. So entrainment of liquid droplets can be avoided by providing suitable demisters. Okay, so this is CS is column support, BP is baffle plates. Okay, this is called baffle plate. Okay, so normally at the inlet, liquid inlet, you have to provide this type of liquid inlets. Otherwise, what will happen? It will disturb the tray dynamics or sometimes stability of trays. Okay, so you have to provide this type of baffle plates. Okay, so different type of feed inlet nozzles we will discuss later. Okay, so tray or plate column, it should have a vertical cylindrical cell and it should have set of tower internals. The tower internals may be trays, that is the heart. Then you have to provide the arrangements, provisions for flow of liquid from one tray to another. Okay, so that's called downcomer. Then you have to provide the inlet and outlet nozzles. These are the major components. With respect to design, we have to design the column diameter and height of the column, and also we have to check, we have to design the downcomer, wear plate, those things. Okay, so the cell can be made up of this metal, this MOC can be metal or sometimes it may be alloy. So this cell may be a piped cell or plate cell based on diameter. This can be done. So we have discussed this piped cells and plate cells in heat exchanger. Okay, So if it is available in the market as pipes, then you can use pipe cells, or you can make this cylindrical portion using a plate cells. Okay, single seat can be converted into a cells. Okay, like cylindrical, like this. Okay, so you have to roll this and you have to make the plate cells. Okay, so the material of construction, whether it's metal or alloy or whatever maybe, or plastic. Okay, so that can be selected based on the corrosiveness of the fluids, temperature, pressure, and cost. Okay, so if you have column diameter is very small, then what you can make small sections, then they can be connected with suitable flanges. Okay, these has to be connected with suitable flanges. Okay, so tray columns normally will not be selected when the diameter is less than 1 meter. Most of the times it's used for column diameter more than 1 meter and greater than 10 meters. We will go for tray columns. Okay, so with respect to tray, you should know about tray support rings, support the trays inside the column. So tray support rings are nothing but metal angles as like this. Okay, so this is your cell wall. So this is your tray support rings. This has to be welded. Then this is another side of tray or cell wall. This is your tray support ring. This has to be welded or bolted. So over this you have to keep your tray. Okay. So like this you have to make this tray support. Okay. As I said, big diameter trays you need support beams. Instead of this tray support ring, it's like a circular one. Okay. So you have to go for beams, whatever we are using in buildings. Okay. So these beams you have to use to support the rings, because it has to withstand this dead weight of the plate. These plates are nothing but circular one. Okay, circular plates. So based on this thickness, the dead weight of the plate will increase, so the column weight will increase. So we have to do suitable stress analysis in the column, and we have to select the thickness. So thickness of the cell. Okay, so this thickness of the plate. So we will make so many holes over the plate. So again it will decrease the strength. Okay, so we have to consider everything. Then another component is skirt support, as I said. So the column weight, liquid load, wind stress, seismic factor, everything has to be considered when you design a support. Column weight means the dead weight of the column, empty column. Okay. Then with liquid you have to check the weight. Okay. Then sometimes if it is very tall columns, what will happen? So if this is the wind, okay. So you might have studied drag. Okay, rho u square by 2. Okay, this drag. Okay, so you have to make suitable calculation to account this, because this will make a bending moment at the bottom. Okay, so if it pulls the tall column like this, then what will happen? Here it will create a stress. So what tall columns, what they will do, the bottom they will have a bigger diameter, and so that you can see this will be the columns or tall columns are designed like this. It's especially chimney or even dams, you can see the bottom the thickness will be more, because the stress will be more. So you have to study suitable you have to do suitable stress analysis to account the wind. Sometimes if it is for example USA or Europe, what will happen? The snow is the another problem. So it will increase the dead weight of the column again. Okay, so you have to account those things also. Then seismic factor. So if a particular place is repeatedly suffering to earthquake, then you have to account this, and accordingly you have to provide the skirt support. So all these things has to be accounted during the design of support. Apart from that, additional accessories like ladders on the cell wall, then platforms, then you have to provide insulation, suitable insulation, then you have to provide manifold. Okay, then you have to provide side glass. Okay, you can see what is happening inside. So you have to provide side glass. Okay. So all the arrangements that you have to provide these columns, type of tray columns. Okay. The tray may be a bubble cap tray, wall tray, or sieve tray. Okay. So we know the functions of the trays. So the trays are the heart of the column. Okay, trays are heart of the column. Okay, so this different type of trays we will discuss in the next class. Okay, so do you have anything you want to share?
Sir, again you are following that book only, sir? Coulson and Richardson or
Yes,
some
here
other one?
volume 6, or and you can also refer tray ball, mass transfer operation. Tray ball.
Okay. Yes, sir.
And also you can refer M.E. Joshi for this mechanical design. Okay, absorption, distillation, those things. Anyway, we will discuss one day this mechanical design. Okay. Mostly you can refer CR volume 6. That's enough. Okay, for mass transfer operations. Dryer you can refer tray ball. Okay. So anyway, when you solve the problem, you will get the concept. Anyway, CR volume 6 is we can take as the reference for gas liquid or the tray column and packed columns. Okay.
So chapter 11, sir,
Yeah,
in CR volumes.
yeah. Okay. So can I stop at this point?
Sir, okay, sir.